Welcome back, students. I hope you enjoyed Chapter 8. Now let's begin Chapter 9, which goes one step further. The fundamental difference between Chapter 8 and Chapter 9 is this one right here, whether we know the sigma value or not. In Chapter 8, we assumed we knew the population standard deviation sigma. In Chapter 9, we don't. Does it make some difference? Oh yes, it does. We already have some uncertainty regarding mu because it is unknown. On top of that, we have another uncertainty because we don't know the sigma value either, and we're replacing this population standard deviation sigma with a sample standard deviation s. Consequently, the inferences we are doing in Chapter 9 will be less accurate than those of Chapter 8. More precisely speaking, we should be a little bit less confident about the inferences in Chapter 9. How less confident? Well, I'll show you the picture in a moment, but let's summarize our discussion kind of like this here. In a nutshell, we're talking about inferences concerning the population mean mu, and here's the key question. Do we know the sigma value? If we know the population standard deviation sigma, and the population is believed to be normally distributed, then we can use Chapter 8 method. Standard error is sigma over square root of n, and we used the z-table and z-curve. Now, what if the sigma value is unknown? Assuming the population is normally distributed, we can use similar method where the standard error is s over square root of n instead of sigma over square root of n, and we use t-curve instead of z-curve. Now, what is so-called t-curve? Let me show you. In my notebook, oh, by the way, this is the same checklist we just went through. And here is a comparison between the t-curve and the z-curve. The red is z-curve, and the t is the t-curve. But t-curves come with something called the degree of freedom, which is n-1. Sample size minus 1. For example, if the sample size is 20, the degree of freedom is 19. If the sample size is 15, the degree of freedom is 15 minus 1, 14. Be warned, the degree of freedom is not always n-1. In this case it is. In 1000 level, most of the time n-1, but there are some examples that things behave very differently. This program comes with an animation, and as you can see, the t-curves merge to the z-curve, converge into the z-curve as we take bigger and bigger and bigger sample size. The degree of freedom is increasing. As it increases, the t-curves converge to the z-curve. So if the sample size is sufficiently big, something like 100 or something, in that case the difference between the t-curve and z-curve is going to become very small, meager, and we'll simply use z-curve. Here's another visualization. This time let's look at confidence intervals. The blue and red represent the confidence interval, 95% confidence interval given by the t-curve of degree of freedom 4, which is associated, of course, to sample size of 5. 5 minus 1 is 4. On the other hand, I hope you can see those gray curve, and that's the normal curve, z-curve. And the starting and ending point of that 95% confidence interval for that normal curve case is given by this dotted line segment here on the left and then there on the right. As you can see, the blue confidence interval for this t-curve is significantly bigger. Now what if we increase the sample size, kind of like this? As expected, almost no change. Early on, significant change between the normal and the t-curve. Something like n equals to 50, almost no difference. Well, the normal curve, the z-curve, didn't go anywhere. It stays here, but it's just that the t-curve was grabbed almost on top of it, so we can't really see it. As you can see, the dotted line segment and solid purple line segments are so close to each other, we cannot really see the difference between one and the other. And if we take a little bit medium sample size, like sample size of 10, some difference, but not as big as smaller sample size, kind of like this. Same behavior exists for confidence bounds too. We have just the same kind of T-curves, except that we had considered just one endpoint here, lower confidence bound, and then one endpoint there, upper confidence bound. Well, so much for visualization. Let's go ahead with an example here. Here we have a data set of 13 adult women's pulse rate. And from these we can find out the mean and the standard deviation. For example, here's the mean. Oh, excuse me, I want decimal. 75.6923, and this is standard deviation, or sample standard deviation. Again, I want decimal. 14.5395 approximately speaking. And here's a reminder, by the way, how do you calculate the this standard deviation or sample standard deviation? We begin with variance first. 83 minus the mean deviation squared plus the next number, 58 minus deviation squared, and then the next one, dot, 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 and then 108 minus mean squared, so deviation squared plus dot, 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 and so on, divided by 13 minus 1, the degree of freedom. That's going to give me the variance if I take the square root of everything, and that's going to be the sample standard deviation. If you do this right, you're supposed to get 14.5395 approximately speaking. Okay, let's find out 90% confidence interval and then 98% confidence interval. How do we do that? The very first thing you'll have to do is draw a picture. And here we go. Here's the picture. We have 90% in the middle and consequently 5% to the left and 5% to the right. And we have all the answers here, but don't pay too much attention to these. The first thing you'll have to do is to check the center. That's gonna be the sample mean, 75.6923, and 90% in the middle, 5% here, and 5% to the right. Now what do we do with this? Well, we have to find out these endpoints here or there, and I found it a little bit more convenient to do it with the right hand side. Basically we want something like this. End minus center over standard error is approximately not z-score but t-statistic. Now, if this had been z-table, we simply set z equals to something, looking up the z-table. This is for t-curve, so we have to look up the t-table. And let's discuss how to look up the t-table. By the way, we have discussed everything so far. The sample size and degree of freedom is 13 minus 1, so that's 12. And sample mean, sample standard deviation. And then standard error is sample standard deviation over square root of n. And if you do this computation, you're going to get 4.03 something. Okay, now here is the t-table. And t-table looks very much like, the t-curve looks very much like z-curve just by looking at it qualitatively. But there is a significant difference between one table and the other table. The shading is to the right hand side. Here's the z-table, by the way. The shading is to the left hand side. The first page, second page. See the difference? This is the Z table, and this is a T table. Shading is to the right hand side. And that's why I'm doing the right hand side endpoint first. Okay, now how do we find out the t-score? First we find out the degree of freedom. The sample size was 13, so the degree of freedom is 13 minus 1, that's 12. And then let's go back to the picture. 90% in the middle, 5% to the left, 5% to the right, right, that's 5%. And let's go over to the t-table. The shading is supposed to be right hand side, so we have to look up the 5% in order to use this shading. Now where is the 5% or 0.05? Well, this column here, and consequently the corresponding t-score for 5% shading and the degree of freedom of 12 is 1.782. That is the t-score, 1.782. In short, this one and minus center over standard error is supposed to be 1.782. That's the t-score, but by the symmetry we have the same thing on the left hand side as well, so plus or minus 1.782. We have done this before. In a z table we do the same thing, plus or minus z-score. Here plus or minus that t-score. That's it. And minus center over standard error. Center is 75.6923 and standard error is 4.03 something, and set this equal to negative 1.782 or positive 1.782. Solve these and you're gonna get this endpoint 68.5063, 82.8783. Those are the endpoints of this confidence interval, this one and that one. In the end, we get this kind of confidence interval, 68.5 to 82.9. Now, can you do the same thing for 98% confidence interval? Well, I don't have any solution here, but I can help you with this visualization. Instead of this 90% confidence interval, let me draw 98% confidence level, and here we go. As you expected, we have bigger blue portion here. 98% goes in the middle, 1% goes there, 1% goes there. You'll have to follow pretty much the same step-by-step process in this solution, except that this t-score has to be associated to 1% in the right-hand side, not 5%. So plus or minus something will be not 1.782, but it should be associated to 1%. So here in this column, and degree of freedom is 12, we need 2.681 something. Replace this one by 2.618, follow through, and you'll be able to get this done. The detail is left to the students. Here, let's go back to 90%, the way it was before. Oh, by the way, if you're looking for, say, 95% confidence interval, the same deal. 95% in the middle, and 2.5% on the left, 2.5% to the right. So you have to look up 2.5% in that t-table. Okay, how about confidence bound? We're in this kind of situation. To the right hand side we have 5% because 95% is there. Basically the same kind of technique. In the same t-table, look up 5% there. How about the lower confidence interval? Well, this left-hand side is 1%, but then again, we don't have this left-hand side shading in this t-table. So what do? Look up appropriate number to the right, and then simply take negative of t because of the symmetry, it works out. The detail is left to the students.